Hello, everyone. My name is Giannis Gonidelis, and today I'm going to talk about parallels on ranges. Now, first of all, a couple of words about me. I'm an undergrad from Greece, where I'm currently pursuing my bachelor degree in electrical and computer engineering. And I'm an open source contributor in Stellar Group, where I'm mainly involved in adapting our HPX Parallel algorithms in the latest standard, that is C++20. Stellar Group is a research group based in Louisiana State University at the Center of Computation and Technology. Steven is a member of Stellar Group too. Our two main projects involve HPX and Phalanx. So today, what I'm going to talk to you about is how we could parallelize ranges and whether should we. First of all, I'm going to introduce you to how we got from simple algorithms, STL algorithms, to the concepts of ranges. I'm going to introduce you to HPX, which is a C++ standards library for parallelism that you probably need, but probably, again, never heard of. And of course, in chapter 3, I'm actually going to explain you all those challenges that are imposed by parallelized ranges. I'm going to demonstrate you with a couple of results and make a few propositions for future work. So let's begin. Okay, algorithms and ranges. So first of all, until 1998, C++ programmers had literally nothing in order to code their sequences. They didn't have algorithms, they didn't have data structures. And now 1998, standard template library gets standardized and certain algorithms and containers are being introduced, and along with containers are being packaged in a way that now it makes every C++ programmer's life far more easier. Fast forward to C++ 17, where the parallelism technical specification is being standardized. And now, not only do we have actually out-of-the-box algorithms to use, but those algorithms, those STL algorithms, can now be run in performantly. Actually, we could port certain execution policies to them that have been exposed by this technical specification. So whatever has to do with parallelization or vectorization or the combination of those two can be actually ported to the algorithm in a very intuitive and readable way. So I would like to note here that it required for the APIs, for the algorithmic APIs, just one additional argument, the argument of the execution policy. And your code would then run in parallel and it would be far more performant than it used to be. So on the good side, you would let your system manage your parallelization, and it was very readable. But on the drawback side, you had to let your system manage your parallelization. In other words, you didn't actually have a word on how your whole sequence would be parallelized. So until C++20, what we had was the great tools of the standard template library and possibly performance tools. What we were lacking, though, was composability in a way that we had to code every sequence in a single step. And of course, we didn't even have performance composability. So I'm going to take it a step back and introduce you to Range v3. For those who don't know, Range v3 is a third-party library that is being developed by Eric Niebler and has been partially standardized in C++20. And its two main advantages is that it exposes composability. It allows for the programmer to code multiple algorithmic operations in a very composed way. And of course, composability makes code far more expressive and far more readable. The code became more intuitive. And these are actually the main two aspects everyone keeps talking about when they're referring to Range v3. So today, I'm going to actually explain how this composability leads to great performance potential, how this chaining of the operations can actually be scaled in a parallel way, and how range v3 actually didn't make only our code readable, but has the potential to make it much more faster. So I'm going to take it a step back again. And for my beginner audience, I'm going to explain what a range is. So it's an abstraction of our data. It's an abstracted way of presenting our data. So we move a step back from the concrete data structures that we had until ranges, and it's actually a sequence of items that you can iterate over. And these are the only constraints. If it's a sequence of items and you can iterate over it, it's a range. Of course, there are some certain specific requirements that are dictated on the specification, but for the beginner audience, that's enough in order to understand what a range is. It's an abstracted way of representing our data. It's very intuitive. On the implementational side now, a range is actually a pair which denotes the begin and the end of the range, the begin and the end of our sequence. So this pair is a begin iterator and the sentinel, where the sentinel could either be the exact same type with the begin iterator, and that was the case until ranges got standardized, or now with range v3, it could either be a value or a distance from begin. It gives us more options, and it's an expansion of the rule of how we represented data until C++20. So I will actually show you a graphic example on how ranges work, how ranges are being composed. So C string was the initial idea where range v3 got built on. In other words, range v3 range v3's initial idea was that with a C string that we assume already may know, we have this null terminator. So let's say I wanted to make a certain operation with my C string. What I need to do is to actually iterate over the C string twice. The reason was that I need to actually spot the null terminator and actually find the size of my C string, and then actually apply my operation. So this required two passes. And this was the case until range v3. Now, with the begin and end iterator, as I previously explained, which are of the same type, you can have your range. But now range v3 lets the user to denote their data structure with just a value. And this is a C string, and it's very intuitive, as you may see. So the begin iterator and until when you find null terminator would just work with range v3. Also, you could just say, no, I don't want until a certain value. I just want from begin +2, and that's also a range. So as you may understand, the pool of options that the user now has with ranges in order to represent their data is far more flexible, far more intuitive, and it's actually great. Now, let's see how range v3 actually achieves expressiveness on our parallel algorithms. What would you do without range v3 is what you needed to do actually when you were calling an algorithm is that you were always asked to provide the begin and end iterator. So this is a simple find, but there are other algorithms that include that are actually like stud copiers to transform that require more iterators to be used. So you had begin and ends all over the place, and your actual algorithmic operation was just a small part of the screen, and it was not readable. The user had to actually sit down and understand what this was all about. And now range 3 comes and saves the day by just letting you port your single range in there, and it would just be the same result. It was very intuitive, it was very readable, and now my friends were asking me, hey, I don't want the whole vector, but of course, you probably wouldn't be able to do that even before range v3. You always gave a begin and end. Now with range, you could either give begin and end, you could either give your whole range, or you could give just a sentinel value and say, hey, I want you to look out for 3, only from the beginning until 4. And in this way, we are alleviating from using just the same begin and end type all over again. Of course, the result would be the same. So that's how range v3 actually achieves readability. Let's go on the composability side, which is far more relevant for this talk. So say I have a vector, a simple vector, 1, 2, 3, 4, 5, and I want to raise the elements to the power of 2 and remove the remove the odd ones and keep only the even elements. What I would most probably do before ranges got introduced is that I would use a couple of standard algorithms, a bunch of iterators, and one or two copies. With range v3, our code converts to this very beautiful and intuitive sequence. So there are certain elements here, for those who don't know how ranges work, that may not seem familiar, but the code is smaller and it's more expressive and it's composed. And I will explain actually how you could achieve the same results with this composability in the next slide. So how does range v3 achieve composability? There are these 3 major elements. First of all, ranges are heavily utilizing views. Views are lazy algorithms that are evaluated on demand. And I literally can stretch out how important this is. A view is a projection of the operation that I want to do on my range to the future. And what's the future? It's actually when I only need that range. So my particular variable RNG here won't be calculated until I actually need it on line 7. So when I call it on line 7 to actually output it, to be outputted, that's when the transform and the remove if will take place. And the various range adapters, which are the minimal constructs that actually compose a range, will be pipelined throughout the pipe operator and will give me my final range. I want you to understand before we move forward, this is all introductory stuff, how views are being calculated lazily and how range adapters are being composed by the pipe operator usage, which, by the way, it's very intuitive since we've all written bash scripts. So C++20 range v3 is getting partially standardized. We hope that in C++23 we get more of range v3. And composability is a problem no more. So the question remains, can we now actually combine composability and performance? What I previously explained to you is that with range v3 we have the composability aspect, but as you may have understood, we cannot port execution policies in there. So this is the main question that has to do with this talk. I'm going to turn the page and actually introduce you to HPX, which will help us enable performance composability. So HPX is a C++ standards library for concurrency and parallelism. And there are 4 major takes here, maybe 3. First of all, and maybe the most important one, is that we are standards conforming. Standards conformance is our motto, and actually, I can stretch this out enough. You could literally write your code and change your stud : namespace to HPX : and everything would be functional and would be working just fine. We provide the exact same APIs. But that's not even the best case. I mean, with HPX, we're not just re-implementing the whole standard there just to show off. We are providing you with all those performance tools in order to, when you change your code from standard to HPX, you are being given certain tools that help you achieve far greater performance. HPX is also a general purpose library. That means you can take HPX and apply it to a mini parallelization script on your laptop, or you could even use it on large-scale physics experiments that have to be executed on clusters with heterogeneous or distributed computing involved. Now, what HPX actually does is that it enables both parallelism and asynchrony. So just for the parallelism part, we are, as I said, we are standards conforming. So we are still pro auto-parallelization. We are giving you that. We also provide you with the whole set of parallel algorithms. And we are very proud of that because we are one of the few standard libraries that actually give you those parallel algorithms. And we are very fan of asynchrony. And how we achieve that is by using futures. Some of you may already are familiar with futures. Futures is a feature of that got introduced to C++11, I think, and it helps us achieve asynchrony. Only that our futures are far more heavyweight and actually give more flexibility to the user if they have more operations and whatsoever. I will dictate our execution model in a couple of lines, and we'll demonstrate you some examples how you actually get far more better performance when you are exposed to asynchrony. So we hate static scheduling. That's a thing. We actually love reallocating work on the fly, and it's actually very intuitive. So if you think of it, you don't need to have a static scheduling that you actually create it before your work initiates and go by that, but whatever happens. You could reallocate work whenever your threads are available. You always keep your threads busy, and that's, of course, more performant. And I will demonstrate you with this very, very simple example how this achieves greater performance. So let's say we have a 4-core system and we have a certain amount of workload to do. And with your everyday parallel runtime system, what would you get is a static scheduling, which would, of course, impose certain barriers. Now, what you get with those barriers is idle threads all over the place. I mean, literally, there is a lot of empty execution time in there. And the conclusion is that barriers are bad. So what we try to do in HPX is that we try to create a dynamic scheduling of our tasks. And the best part is that we reallocate work when a thread is available. So whenever there is availability of resources, your work gets reallocated, and the result is more work done in a smaller time frame. So that sounds pretty intuitive. And why shouldn't we do things like that? Things should change in the parallelization and asynchrony domain. So HPX, being standards conforming, of course, provides you with all the execution policies that you had in C++ 20, with namely parallel, vectorization, whatever. But it also now enables the asynchronous execution policies. Now you are only seeing the asynchronous parallel execution policy, which is my favorite. But of course, with this parenthesis task tag that you could just put next to whatever execution policy of yours, you would actually let your code be executed asynchronously. We keep the readability advantage with this way. We keep the readability advantage, but now we are also letting you have a word on how you want your work to be parallelized. The user now is responsible and is actually in full control over their parallelization. And here's a very representative example of how that is achieved. So with the futures, with futurization, what would you probably do by using HPX is that you would initiate your work with either an HPX async command call, where you would just call your function with HPX async, or you would either port your asynchronous execution policy in there. The important thing is that you would allocate your result to a future variable. So as you can see, I now keep an F, which will just tell me when my work is done. So I have initiated my work, and then I proceed in doing whatever I want to do. I mean, literally, I can do anything. I have pushed the work behind the curtains. I'm not blocking the execution. I'm not imposing any barriers at all. And I'm only asking for my results when I actually need them. It's very intuitive. That's what I'm trying to tell you. So with this .get command, you actually block the execution only when you need to, only when you can't move forward without this result. And it gets far better. With the .then command, you could actually attach continuation to this whole asynchronous execution. So you would just say to your system, run this thing asynchronously, run it whenever you want it and whenever you think you have free threads. Don't block my execution. And when you finish, do whatever is inside my then parentheses. So that sounds pretty performant to me. So I've been rambling about how we are all full about standards conforming in HPX and how we advocate for asynchrony. But I haven't really explained to you how our algorithmic families are one of our advantages too. Actually, my job on HPX is to work on the algorithmic families. And I'm going to show you how being standards conforming plus more gives the user a lot of potential. So the parallel algorithms, just out of the box, just like you had them in C++20, are exactly there. You just need to change your stud namespace to HPX namespace. You port an execution policy in there. It runs in parallel. It's great. Now, you can also run it asynchronously, a thing you can't do in standard C++20. And you are also enabled with the ranges overloads that got recently introduced. So let me be explicit about this. When the ranges got partially introduced, it allowed us, for those who don't know, to compose our data structures more nicely, but it also gave us certain ranges algorithms because we needed standard APIs to run things. So we are one of the few standards libraries that actually provide you with the ranges algorithms. That's what I'm working on. It's an ongoing project. We haven't finished yet, but we are very optimistic on finishing this task by September or something. So these are the great big algorithmic families that you can use when you're using HPX. And I want you to keep those in mind while I'm proceeding on how we could parallelize ranges. So whatever I'm going to say from that moment on applies to all those three algorithmic families. You could do all those things. So if you use HPX with C++20, you are actually enabling real performance there. And now let's solve the problem of performance composability. I've introduced you HPX. I've introduced to how ranges are having certain advantages and how we got to them. So let's see the problems and how, if we could parallelize them. So the initial step, of course, was just to achieve C++ conformance as a third-party library ourselves. We, as I've already told you, provide you with the standard APIs, the exact same code. You just change your stud namespace to HPX. It runs perfectly. You could port a single range in there or a beginner iterator and a sentinel, and it would run just fine, only that it doesn't actually support execution policies yet. So let's see first how those execution policies work on a standard parallel algorithm rather than a range parallel algorithm, rather than a range algorithm. Sorry. So with a simple for each call, you would get your begin, end, you allocate your work, you would distribute according to your resources, and this is it. This is simple. So if you just give to your system a single range input, the only problem is that the system has to be able to translate this single range into begin and end iterator and just dispatch it again to the base implementation. So there's not much work done there. Actually, we just provide you with a higher level abstracted API that accepts a single input range. And with those HPX util begin and end facilities, we dispatch the range to begin and end iterator of the same type. That's important. And we're just calling our base for each implementation. Okay, we can get it a step further and actually say, okay, if I want my begin and end to be different as range B3 dictates, then what's the solution? Well, okay, begin stays the same. It's an iterator. Now, Sentinel could be whatever, a value. It could be an iterator itself, or it could be a distance. So there it gets a little trickier, but with a little tweaking with ranges facilities, like we need to calculate the distance between begin and end, and that's not trivial anymore since their types are not uniform. We create in the base implementation a new end iterator. We calculate the distance, whatever, we split the workload, and things run in parallel again. Okay, now I previously said that the base implementation could stay the same. Now the base implementation, of course, changes. So yeah, the base implementation is being adapted accordingly. And I want you to understand that this is a broader scenario of actually having a single range input, because we enabled the base implementation to actually accept both, to actually accept different types. Okay, that's very important. So supporting different types is broader than supporting the same types. This code would just work fine with this base implementation would work fine with a single range input. So we've solved that in HPX. We have achieved that with whatever algorithms we have adapted, and we will achieve it, of course, until September. And I want you to actually take a minute here and to consider this is happening right now. HPX does provide you with ranges algorithms being executed in parallel. You could just port a single range input or port an iterator Sentinel pair, and it would run in parallel. Okay, so this is important. But that's not the final goal. Let's see what the final goal is. I was rambling on section number 1 about how those great sequences achieve composability and expressiveness, whatever. And I hear your demands. You want those things to be ported into your algorithms, and your algorithms to run in parallel. And that was the final goal. That's what initiated the idea for this whole talk. This thing does not seem like a concrete data structure, a concrete type that you could just split your workload and parallelize it. It even includes operations in there. I can see my range, my input range to be applied to certain operations. So it's not trivial. It has some pipe operators in there, and let's see how parallelism could actually be achieved with those inputs. So the first idea was that we could actually code every algorithmic pair of those views operations. We would actually provide implementations behind the curtains that would dispatch to whatever you gave to the library. So you gave a transform and remove if. We had an implementation for that. You gave a sort, the pipe fill, pipe transform, and we had an implementation for that. And since we had this implementation, we could just provide parallel implementation. This would be great. This would be straightforward, but of course it would require hundreds or thousands of combinations to be implemented. So that's not an option. If you think that's implementable, be my guest, but there are far more better options here. The second idea was that we could actually utilize the classic fork join parallel that I previously talked to you about. So again, on the classic transform remove if example I keep talking about, you would just parallelize your transform in a fork join mode, and then wait for it to complete, and you would parallelize your remove if, port your sequence to wherever you want to port it, parallelize your algorithm. It's fun, but it includes barriers, and HPX hates barriers. And actually, that's not the reason that we rejected this idea. Rather than there is a better option on that. But please consider the fork join option, because I will come back to this on the last slide. What range B3 actually gives to us is a fusion of those operations. I don't know if I'm making sense. So let me demonstrate you how that's being achieved, this fusion. I previously talked about how range V3 has those three basic these great assets of views, range adapters, pipes. Those all are great. But what's greater, and I don't think C++ community is considering, and is actually, that's what I'm evangelizing about. It's that range V3 exposes inherent fusion. So when I saw that for the first time, I was like, okay, I get my VI vector ported to this transform operation. I will wait for the transform to end, and then the remove F will be applied, and then this thing will be ported to my algorithm. But as I said, views are projections to the future, are descriptions of your operations on the future. So they are being actually applied when you only need your range. And since you are porting this range into an algorithm, you can't wait for the whole range to be calculated and then applied to the algorithm. So this great idea of Eric Niebler himself is that he fused the operations in a way that they would be applied on an element by element basis. This is extremely important. I can't stress this enough. You give a transform and a remove if operation. These operations are being fused and they are being actually applied to an element by element basis. Now, all I'm seeing here is a single operation. I'm seeing a transform underscore remove underscore if operation. And that sounds like parallelizable to me. And I tried it actually. So the way to enable this fusion is to actually call the range within the context of a parallel algorithm. This is simple. This sounds parallelizable. Could it be parallelized though? Let's see. There are these hard and easy to parallelize combinations as our experiments showed. So these bad and good cases, which I don't think it's a good naming solution, but they make our life easier when we want to parallelize them in the easy case and harder when we want to parallelize them in the hard case. And the reason why parallelization is not as trivial as I just described previously, of course, it's not trivial, it's not standardized yet. It's because those operations still remain mathematical algorithms, like algorithms that need to have actual implementations. Let me explain myself. When I use and transform and remove it, yes, I said it's a single operation and I was very happy about it, but it's not like that we get the full of those fusion. We get the whole advantages of this fusion. When I apply a transform and I remove it, I expect from my range to be resized and from elements to be removed from this sequence. And actually remove if exposes a bidirectional iterator. I think you all know what iterator, how the categorization works on the iterator side. So the bidirectional iterator just lets you move forward and backwards on ON complexity, rather than a random access iterator, which would just let you hop between the elements on O1 complexity. And O1 complexity is what a parallel system would ask from you if it needs to parallelize your sequence. This bidirectional iterator that's being exposed, since it's weaker from the random access iterator, which transform probably uses, makes parallelization harder. And when you want this sequence to be parallelized, it actually gives you worse results. But on the other side, a simple transform reverse, which is extremely trivial if you only think it just out of your mind. I mean, transform this thing and then reverse this thing. There is no resizing. There is just you just change the elements in there, and it's very trivial. So actually trying to parallelize that would be far more easy. Of course, there are a couple of other things that have to do with iterator exposition, but I want to be explicit on those. It's that certain algorithms would include a temporary usage, or there are this adjacent family of algorithms that have predicates that are related to multiple elements. So adjacent works on consequent elements, so I can move with my parallelization without knowing my element next to me, and so on. And these are the main two problems that I want you to consider when actually asking for range parallelization. So it's the problem of iterator exposition, how parallelizable those single operations are. Let's see how HPX now works on top of range v3. Now, I say to you that HPX provides the ranges algorithms with execution policies. This was, at first, this was just an API problem for us. But as the results showed up, you could just actually create this sequence and port it in there and run it in parallel with our ranges algorithm, which are the only ranges algorithms that support parallel execution policies, and it would run. I mean, it would execute just fine. Now, the only question that remains is, would it run better or would it run in a worse way? So we could actually take advantage of this inherent fusion and create parallelization, but the result is that you have to actually be cautious about what kind of combination you are using. And I'm going to propose a couple of solutions to the end of this talk. So with HPX on top of range v3, not only can you parallelize your everyday usual ranges, which could be either a vector or iterator sentinel or whatever, but you could actually take those sequences and run them in parallel, those composed sequences. And I want to be explicit on that. This thing, at the moment we're speaking, can actually run on your computer. You can just download range v3 and download HPX, compile them together, and the script that I showed previously works. And that's important. So there was this question that Terry asked on one of his podcasts, and it was very interesting. He said, "Hey, ranges seem so simple to me. Couldn't I just port them to my parallel algorithms?" That's what we thought, and we created the parallel ranges algorithms, of course. But why not port them to the standard parallel algorithms? Well, number one, of course, there are no APIs exposed yet. If they will be exposed, be my guest. But number two, and most important, is that by using HPX, using parallelism from HPX and not from the standard, and range v3 by combining those two, you also get all those benefits that you would get from HPX over C++20. So you get all those futurization and asynchrony advantages. We are dedicated to performance and parallelism. So your everyday compiler vendors of the standard library may not be that focused on the performance aspect. So the final result, with HPX and range v3, you have all the great benefits of composability, performance, standard template library whatsoever. So let's see now how these results actually work. I'm going to wrap this up in like 3 slides. So a bad case, I've been talking about this from the beginning of my talk. It's a transform and remove if example, which I work towards very, very, very hard in order to understand why is it so bad. So I scaled it to my computer and it didn't scale well. And the reason why it didn't scale well was this iterator exposition problem that I explained to you. Now, sounds a little bit vain. I've been talking about parallel ranges and then I demonstrate you with this bad example, but it's in 100 million elements, a vector element. So it would worth being parallelized. And it's a quite trivial case that we would actually want to parallelize in the future. At this moment, there is no performance solution for that. But what there is a performance solution for is this other part where there are some good examples like the transform or the accumulator I mentioned previously. And there is a whole bunch of examples, by the way. So if you can spot those, and we are actually working on that, spot all those combinations that could be parallelized perfectly. If you just port a simple execution policy in there, this API dispatching thing would work fine. And I counted it and it scales great. So it's all a matter of what combination you're going to use. Now, I don't want to leave you hung with these bad cases. I know it leaves a bad taste. So as I said, this fork join idea is bad as barriers are concerned, but it's not as bad if it's the only solution. So since this fusion parallelization example won't work, this inherent fusion can be utilized in order to achieve parallelization, we could think as a C++ community to actually provide certain implementations that dispatch to fork join parallelism when certain operations that are fused are being parallelized separately. So this would require a lot of work because you want to keep your composability on the top layer, and you want to dispatch and actually separate those composable elements to mini parallelized blocks. And it sounds like a lot of work, but it would certainly work on the bad cases. There is also this proposition of using future executors that do support pipeline. That's a coincidence, but they do support pipeline, and they could be actually be utilized in order to achieve asynchrony on those composed operations. Now, let me close this thing and answer to my initial question. Parallel on the edges, should we? It doesn't sound trivial, but then we have those good cases which, hey, they run, they are fast, why not? But you then have to think all about the iterator exposition and, should I do it? I don't know. Should I even waste my time on that? But I just can't resist on this inherent fusion that is been lying there. And this is a great thing. And HPX, although again, as I'm saying, it started as an experiment, it actually provides you with performance on this inherent fusion. So my proposal to the committee on whether should we parallelize ranges is you should probably think it. We should probably think it. It's worth trying because having composable code and performant code is very important in 2020, 2023. Thank you very much. This was my talk, so I will probably accept a couple of questions now. Let me see. Does HPX work with thread pools? Yes. As far as I know, it does work with thread pools. I can give you more information on that. So can this work with GPU? Does it play with new Intel DPC? I can't answer you about the DPC thing, but I know that we are actually exposing heterogeneous computing solutions to our code base. I've heard about utilizing Cocos or something. I'm not involved in that myself, but I know that we do provide solutions for that. Could you quickly go back to the slides with the range P3's views? Okay, give me a second just to answer whatever question doesn't need go running back. Do you think there is a better interface to specify execution policy than an optional first argument? I actually advocated in favor of this solution by only just providing this single additional argument is great. And no, I don't think there's a better solution, but there are certain occasions where you would actually this solution would not be sufficient. So on the asynchrony side, as you may see, you actually need to do more work in order to achieve more performance. Of course, I am always in favor of keeping the code simple and not making all these dazzling things just to seem pretty and hey, it runs fast because it looks weird. No, HPX is all about making the simplest things run faster. So let me get back to my slides where anonymous attendee wanted to see. So you said something about going to the inherent fusion examples. I think you mean these ones? I think that's it, but I don't see the question there. So Okay, is there a question on that, or are you just asking for the slides? I think they will be available. Okay. Okay, I think we should wrap this up. Thank you very much, everyone, for attending, and please consider parallelism moderators when you would have to attend some committee meetings or something. So thank you very much. Bye.